Hello, pre-calculus class. In this video, we're going to take a look at logistic functions, which potentially it's a brand new word for you, that word logistic there. It's almost certainly a brand new function for you, right? I don't think any Algebra 2 classes or Algebra 1 classes ever talk about logistic functions, but they are a very useful function group. They're kind of a spin-off of exponential functions, and we'll kind of look at how the two things are related to each other. You can also look in the book, in your pre-calc book 336 and page 337, kind of like show how you can really derive this logistic function from an exponential. But we're just going to kind of talk about how the two things are related and how really logistic functions are more useful than exponentials in most cases. So right, exponential functions you were introduced to probably even like before Algebra 1. But in Algebra 1 for sure we talk about this, right? There's a lot of different examples, right? Exponential functions are things where like it follows a doubling pattern every time, or something gets cut in half every time, right? Those half-life examples in that logarithmic function that we just looked at, right, is an example of an exponential, depending on like what's your input and output. But some examples of exponential growth, right? Mitosis, cell division, you start off with like one cell and it breaks up into two, and then those break up into two more, and then those four all double to 8, and right over time like it just kind of grows and takes over. Compound interest is another often used example of an exponential function, one of the actual like pretty true exponential function examples. And then the classic one that you see in a bunch of different textbooks is this like rabbits, right? Breeding rabbits, where they start with some number in a right population, and they breed very quickly, right? They have a short gestation period. And so we're going to take just a look at a quick example here and say we start with 20 rabbits and they double every 6 months, right? That's a pretty reasonable time. If you start with that many, right, maybe 10 are females and they have a litter of rabbits, right? If they double every 6 months, means they're quadrupling in a year. And your equation would look something like this. Your starting value of 20, 4 is how much it's going, and if x is the number of years, right? I kind of get this equation, which after 18 months, right, 3 times of doubling, you end up with 160 rabbits, which is kind of reasonable, right? And you can kind of see, right, here's your exponential model in here. And if I have this, we can find out like, right, what's f of 1.5, we get this 160, right? That's a lot of rabbits, but if it's a large enough field or something, like that's potentially reasonable. If there's not a whole lot of predators there and there's abundance of food, that could certainly happen, right? But every exponential model, most every exponential model, I should say, kind of reaches a certain limit of usefulness, right? Like this model might be useful for the first 18 months or maybe even the first couple of years, but after we start to get into years 3 and 4 and 5, we're starting to get up in this like, right, there's 20,000 rabbits now. And if you take it off to like something absurd, say like 37 years, you end up with 3.77 times 10 to the 23rd rabbits, which if you actually look, there's an XKCD that kind of discusses roughly this many, not rabbits, but moles. Question somebody asked was like, what would happen if you had a mole Avogadro's number 6.02 times 10 to the 23rd? What would happen if you had that many moles? And this guy, Randall Munroe, takes this off to the very ridiculous extremes of like, what would this be approximately? And you end up with like a layer of moles on the Earth that's 10 times as high as Mount Everest. And if you put them into outer space, it would be a little larger than the moon. And right, they all end up like, yeah, cooking themselves in this big planet of meat and nasty methane bubbles blowing up moles from the planet. And yeah, if you want to read about that more, I'll have a little I'll put the link in there. But right, so this is not great, right? Like this, if I take this all the way out to larger and larger and larger numbers, right, it tends to fall apart at a certain point in time. That's because everything is limited in some way. Everything kind of has some limited, in the case of like a rabbit population, a carrying capacity, something where like you're probably not going to exceed this much. There's only so much space for the rabbits to live. There's only so much food for them to live off of. Eventually predators will start to find them, and right, you end up with kind of some maybe natural spot that it oscillates around. And so most of these exponential functions, right, including the mitosis and right other things, all can be better described with this thing called a logistic function. So here's the general equation of a logistic function. It follows this pattern of y equals c over 1 plus ab to the negative x. And let's go in here and kind of write this down, right? After 37 years, we had, right, f of 37 was like 3.7 times 10 to the 23rd rabbits, and that is just too many. But so in comes this logistic function to rescue us. So here's the general equation of a logistic function. We have I equals c over 1 plus a times b to the negative x is one way to write this. And there's a few restraints, right? C is the upper limit or upper bound on this thing. In the case of a rabbit population, it would be like the most rabbits that can possibly be sustained in the area that we're talking about. But it's this kind of upper bound, and it'll eventually be a horizontal asymptote. You can't ever quite actually reach it. A and b are constants. We need both of those things to be greater than 0 in this case, right? And the domain is all real numbers, right? Everything can go in. And so this, right, if we go back to here, right, this thing, if I zoom in here at the beginning, it looks exponential, right? At the very start of this, it kind of behaves like exponential growth. It's looking like, right, what our rabbit thing did at the start. But if you zoom out and kind of go, it shows that eventually you will hit some upper limit here, this upper bound. So if I have these, I have the sliders A, B, and C kind of all in there. C is just how, right, where am I going? What's my upper bound for this thing? Right, y equals c is this horizontal asymptote. The other horizontal asymptote is down here at 0, right? But if I have this, right, my logistic function is this kind of constrained growth. It starts off exponential, but eventually hits some maximum limit. The a and the b values are a little bit different. The a, right, you can almost think of it as just like a little fudge factor for, like, you know, where are you zeroed at? It kind of shifts this thing to the left and to the right. The larger the a value, the further right it goes. The smaller the a value, the further left it goes. The b value is really a kind of how fast is it growing, right? A really large b value means it's growing pretty quickly relative to your x-axis here, right? A smaller b value, something closer to 1, means that it's growing a little bit more slowly. And if b is less than 1, between 1 and 0, it's actually a decreasing logistic function, which you can have, right? So there are a lot of different things that can be modeled with these types of functions. Okay. So think of anything, right? If I kind of go to something maybe out here, right? There's a bunch of different things that could be modeled with this, right? You think of anything that starts off slow, right, kind of increases in the middle and reaches some high point at some point, like maybe an airplane, right? You're taking off, right, from the ground, from the runway, you get up in the sky, and eventually you reach your cruising altitude. Or a car that's accelerating, right? You're starting off slowly and you hit the gas and it's going up, 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 but eventually, right, you start to hit the top speed of your car and it tapers off until you get right to the closest that it could possibly be. An object dropped out of an airplane, right? And it starts off slow, right? Gravity's pulling it down, accelerating it, but eventually it hits some terminal velocity where it can't fall any faster. Population growth, right? The rabbit example, eventually it's going to hit some upper bound, some carrying capacity. News spreading, right? Think of like a rumor. It starts off popcorn, you have a couple people, and eventually there's a whole bunch of people that are telling everybody, and by the time you're one of the last people to find out, you're trying to tell other people, but they've already heard it, and right, the news starts to spread until eventually maybe the whole population, the whole school, whatever it is, has heard it. One very recent example that's kind of timely in this situation is disease spreading. Right? It starts off kind of slowly, but grows exponentially for a while until things start to get under control, and it'll eventually taper off a little bit. And so that's the example that I'm going to just do mathematically here, right? So we are going to take a look at a case where in the coronavirus data, where it's more or less already played itself out. There's a couple of different countries where their numbers are so small right now that it's basically at the end of it, and Australia is one of them. If we look at kind of Australia's total cases here, there's the data in a couple of different places. Austria was another one where we have this, right, pretty good logistic function, right? So here's the data for Australia, and I kind of looked, right, here's the first few weeks of this, the first like 3-ish weeks. In that time, you can see it is pretty significantly exponential, right? In the first 3 weeks of this, all the way up through, this is like through the 24th, I did a line of best fit for the exponential through this. And there's that graph, this red graph that models it pretty darn close through the first 24 days, right? And so you get this, right, according to the model that I have. On the 24th day, there should have been about 2,000 cases, 2,100. And in the actual data, yeah, there's 2,146. It's only off by like 23 cases. This exponential model was pretty great. But as you start to get further away from those first 24 days, that exponential model diverges greatly from what actually happened, from the reality of the situation. Like, here's the actual data as it played out in Australia, right? And so I did a logistic regression, something in Desmos that you can do. So I have this table of values, the data that I took straight off of, I think Wikipedia actually from the Australia. It wasn't this exact graph, but all of the data by day here. Put it in X1 and Y1, just added the table right in there. And I can make a different logistic function through these exact points, right? So I kind of picked a theoretical cap of about 6,800, the last, right, after 60 days. And this is, right, by the way, this was March 1st. And then every day after that, so that's March 7, the 30th day would be March 30. I think 31 is March 31, and then 32 would be April 1, right? And so this is all the way up through like April 29 or so is this data. But I just picked a theoretical cap of 6,800 because it's leveling out pretty solidly here at the end. And I said, okay, find me what are the A and B values that fit through this data the most. And so to do that, I have to use that actual like Y1, and don't put an equal sign, but put this little tilde. It's usually the top left key on most keyboards, kind of underneath. On mine, it's underneath the escape key. It's approximately equal to, and then I leave these blank. That, right, I put in the C, the best possible C that I could think of. You can leave that blank as well, but it messes with the data a little bit in this case. But I just left those two things blank. Put in this as an X1, and it will give me what is the logistic equation of best fit through this. And you can see, right, that's a much cleaner example. It's actually a little bit worse at the beginning, right? It kind of overestimates how many cases they had at the beginning. Maybe that's an error in the model. Maybe that's an error in the data. Maybe there were actually more cases than what right, you kind of might have thought there would be. And then here it kind of starts to undercount a little bit. So it's not perfect, right? We're working with real world data, but that's a lot more like what actually happened than this red exponential after a while, right? And yeah, I picked. We're gonna do some math in here in a little bit, but I picked, right? If you do the first and last points in here that I have like, right, the first 1 comma 29 and 60 comma 67 53. If I shut this off, right, if I use those 2 points, it's actually pretty far off, because kind of the tail end of this thing isn't behaving quite as logistically as we thought in the beginning too. Like maybe this middle third here is like the most logistic. And so what we are going to do is we're going to try to find, like, show mathematically, how would I get this equation through, I picked 2 points kind of in the middle, March 14 and then 3 weeks later, right? So if I use those data points, we get a much cleaner, right? Again, not perfect still, but a much better example here. So going back to this, we're going to take a look at, all right, an example here. I'm going to just write this down and we'll pop back here in a minute. All right, so we're just going to go through these 2 points and find an equation. We're going to choose a C value to about 6,800, a little bit more than the top actual point in that data there. Right. So if we do this, we're going to create 2 equations just like we always have done before, right? It doesn't really matter which one you put on top, which one you put on bottom. I'll just do the 14 comma 248 into this general equation. So I have y 248 equals C, we're going to choose 6,800, over 1 plus, I'm trying to find what A and B are, and to the negative 14 there, right? And I'll do the same thing for the other point, right? My other point was 35, 5,552. So my Y value, the 5552, will C over 1 plus A times B to the negative X, in this case, 35. Right, so we need to do some algebra, some kind of mathematical manipulation to try to find, like, right, get rid of an A and a B. So we need to do a few things first. What we're going to do is multiply both equations by their denominators. The denominators on the right side. So if I multiply like this by 1 plus AB to the negative 14th on the right side and the left side, it's going to cancel this thing here. So let's just pretend like we did that, right? So I'm going to take that, I'm going to try to skip some steps here, but I'm going to multiply both sides by 1 plus AB to the negative 14th for this first one. So it'll be, right, 1 plus AB to the negative 14th times 248 equals 6,800, right? That, if I have that, right, this times that, it would cancel on that side, and so that's all that I'm left with, right? What happened to my, no? Right, if I did the same thing on the bottom one, I'll have the 5552 equals 6,800 divided by 1 plus AB to the negative 35th, but I'm going to multiply that on both sides. So I have 1 plus AB to the negative 35th out front here. Right. Next thing we're going to do is distribute these, like the 248, kind of through this and through the 5552, through that. Right. There's a few different ways you can do that, but this is what I'm going to choose to do to try to simplify this. Distribute both things here. So I end up with, in this case, the top one would be 248 times 1 plus 248 times AB to the negative 14th equals 6,800. Bottom equation, distribute the 5552. 5552 times 1 is 5552. 5552 times AB to the negative 35th. I just have to write that out. I'm going to subtract the 248 and the 5552, and we're just going to move these over to the other side. Right. So I'm going to subtract those. I end up with just 248 AB to the negative 14th equals 6,800 minus 248. It's going to give me 6552. Right. And then, right, 6,800 minus 5552. 6,800 minus 5552 is going to be 1,248 on this side, and I'll just be left with 5552 there. So now what I can do is I can divide one equation by the other. Right? Because this is going to cancel that A value. That A term. So if I divide this, right, my A's are going to cancel. And I'll be left with, let's go to a different color here, of 248 b to the negative 14th divided by 5552 b to the negative 35th equals 6552 divided by 1248. Okay. B to the negative 14 divided by b to the negative 35. If I do that, right, dividing exponents here is the same as if I were to subtract them. So I have b to the negative 14th minus negative 35. This is going to become b to the positive 21 here. Right? Dividing those exponents, this is just kind of that rule, right? If I have x to the a divided by x to the b, that is equal to x to the a minus b. Right? So this whole thing becomes, if I want to keep it as 1, it's 248 or 5552 times b to the 21st equals 6552 1248. You can put these into your calculator if you want. I just like to work with the fractions because now to get rid of it, I'm just going to multiply both sides here by the reciprocal of this fraction. Right? Right. Because that's going to cancel with that, and that'll cancel with that. And so I'm left with b to the 21st power equals 6552 divided by 1248 times 5552 divided by 248. Right? To undo this 21st power, I need to take something to like raise both sides to the reciprocal of that 21st power. And to the 1 over 21. So this will become, on this side, b to the 21st to the 1 over 21. That's going to cancel. Right? And then this whole thing, I'm just going to put the whole piece here. I'm raising both those to the 1/21st power, but this just cancels and makes, come on eraser. Nope, it's not going to work. Go away. Just B. So let's find out what that is. Right. Go to Desmos here. Right. Open up a new. Right. So I had in there, it was, better make sure I get this right, 6552 divided by 1248 times 5552 divided by 248, all raised to the 1 over 21st power. I get 1.8 1.255, let's call that, right? B is 1.255 approximately, right? Again, this is pretty close to 1, and so again, I want to avoid plugging in these things as early as I can, because right, if this is kind of rounded to some right number, when I raise it to the 1/21st power, that might mess this up a little bit. So I just want to keep exact values until I get to this point for the best possible answer that I have. Right, so there's my B value, about 1.255. I've got it. Now I just need to take that, right, to any one of the equations above that still has an A and find what A is, right? And solve for A. All right, so I'm going to go up here. Let's just take this one and bring it down, because that's one of the last places right before I canceled my A value. So I had 248 times A. I still need to find out what that is, but I know what my B is now. 1.255 to the negative 14th equals 6552. So we just need to get A by itself, right? Well, just divide both. Right? Divide both sides by 248 and 1.255 to the negative 14th. That's going to cancel. That's going to cancel. Right? I just have to do it to both sides. 255 to the negative 14th. So my A value, again, go plug this into Desmos. 6552 divided by 248 times 1.25. 48127, it's that thing up there, to the negative 14th power. I get my A value is 633.9. So that means my logistic function will be 6,800, right, divided by 1 plus 633.9 times 1.255 to the negative x power. Right. So there's my logistic function for this thing, right? Which, if I go back to my original, hey, those are the same A and B values. When I just picked these 2 points to go through, the 14, 248, 35, 55, 52, right? I was just making it go through only those points. It gave me that exact thing, right? So again, first and last didn't work super well, but this worked pretty well, right? So if I have, let's do g of x in this case, because f is my divided by 1 plus 0.9 times 1.255 to the negative x gives me that exact piece there, right? Yeah, so that's how you find the equation of a logistic function, right? It's that constrained exponential growth, and there's a few key points in here, a few things that you could ask, right? Somewhere in between here, right between the bottom and the top, is this point of inflection. And so I'll talk about that a little bit more when I give you the kind of like assignment that I want you to do for this. But right there, that's logistic functions in a nutshell.